Hi everyone, I'm Baryons. Welcome to the 982nd monthly meeting. We have a distinguished speaker today, Anand Narayanan from India. He's going to talk about baryons across time. Actually, I have not met Anand yet. I've spoken to him just now. We have exchanged emails mostly. And how did I come across Anand? When I joined here as the president, sometime in September, we had to fill up the roles of the speakers. So I called a few of my friends. One of them was he's a friend in Rochester. He's my high school classmate, and he's a faculty there. So he said that, remember, we used to go to this observatory in Trivandrum, where I did mention that in my newsletter, a message that that's an observatory which was built in 1834, and this gentleman, Anand, did a nice documentary on it, and he said, do talk to Anand, he may have a good topic to convey. So that's how I met Anand, and here we are. So I think as normally, we would just go forward to the meeting.
Oh, it's time. Come on, Glenn, it's us.
All right.
It's our turn.
It's our turn.
Tell a man there are 400 billion stars and he'll believe you. Tell him a bench on his West plate and he has to touch it. Ladies, is that true?
Yes.
Oh. This man is standing on a mountaintop, sunrise, and he's just inspired. He has a spiritual feeling, so he looks up. God, why did you make women so beautiful? And his voice comes down, so you'd like them. God, why'd you make women so stupid? So they'd like you. Let's see, I had a couple things to talk about. We mentioned that asteroid 877 to Linda. It was a near-Earth asteroid, though it's kind of out there to be near Earth. It has a very eccentric orbit, and again, I've had a lifelong project with that little 3-inch Edmund telescope of mine of seeing how many asteroids I can notch with it. And of course, the low number asteroids, I've pretty well cleaned those up. But this was 877. This was a high number asteroid. And the reason it was discovered rather late is because its orbit is so eccentric that most of the time it's out in a further part of the orbit. It's probably around 12th, 13th magnitude. But every now and then, it'll swing close to the Earth. And we had a very favorable apparition this past month. The next one will be 20 years from now. So this was kind of my last shot. But anyway, I did see it, and because it was moving so fast, I could confirm it in the same night. I just observed every 20 minutes or so, and I was able to see its motion across the sky. And that was asteroid number 120 and counting for the little 3-inch Edmund. Another thing, and then I'm going to turn things over to Rich. How many of you are familiar with this book, Turn Left at Orion?
Oh, yes.
Which is a classic. Again, if you're a go-to person, a shame on you, first of all. But this has got all sorts of charts to find anything. It just happens the two authors are here. Now, Guy, say if I get this right, Consul Magno, is that Consul Magno?
Close enough.
Guy gave a talk at Stellafane. Guy, you can stand up. And new member, Dan Davis in the back right there. So first of all, gentlemen, thank you so much. This is a great resource. In fact, I plugged it in Astronomy magazine, and I noticed that there are there are 3 blurbs in the back talking about how good this book is. And it happens that 2 of them are members of this club. Dennis DeChico wrote one for Sky and Telescope, and I did one for Astronomy magazine. So I don't know where that 3rd person is from. Probably doesn't count. He's not an ATMoB member. All right, is there anything else I had to talk about? No, I guess, oh, yeah, one other thing. Rich and I are involved with this. We did an introduction to the winter sky for new members of the club. Also, if you're a veteran who's been away for a while and you want to just kind of refresh yourself, it was it was fun. It was kind of cold. About 8 people. Chris Elledge helped us out. And we're going to be doing it again in the spring. We'll try sometime in April. You want to try to hit around the middle of the season. We were a little on the early side. And again, it was winter constellations, but Orion wasn't quite up in the southern sky yet. So we could see a lot of the autumn sky still, but we wanted to review the spring constellations. They were kind of lost in the murk. So hopefully we'll have a more central time when we do the spring thing. And now I'm going to turn things over to Rich.
The whole reason for doing these sort of, introduction to the night sky is to just get people to come out and observe with us. We wonder where all the observers are. And so it's just an attempt to get some enthusiasm going, come up to the clubhouse, look through the big telescopes. John Sheff and I were just talking about observing the moons of Uranus with the big telescope. You've never seen those? Come on up to the clubhouse. We see some pretty amazing things up there. And so, you know, those telescopes belong to you all, right? They're the members' telescopes. And so please come up and use them, and you'll have a great time. The next slide is it's my cartoon, actually. I put this cartoon up. I don't know if you've seen this one yet. Pretty self-explanatory.
Yeah.
Right? Right? You get it, right? No? So normal people have 2 kidneys, and in order to afford astrophotography, you have to sell one of your kidneys. That's what it is. Well, yeah. I don't want it to be so obvious. No, that's what it is.
Don't fall asleep at the clubhouse.
That's right. That's right. Don't sit in that red chair. Next thing you know, you're in an ice tub full, a bathtub full of ice. No, it's true. You know, there's also a Ron Burgundy meme that, you know, astrophotography will make you a millionaire if you're already a billionaire. So, you know I'm a proponent of visual observing, and so I make fun of the imagers, but at the same time I marvel at what you all can do with your telescopes and cameras and software. It's crazy. Anyway, so we'll come back to this reason. We'll put that up later. So of course, Alva, you mentioned that there was about to be an occultation of Mars, and guess what? It actually happened, right? Astronomy waits for no one. And so we got a lot of email back and forth. So Glenn had put out a note that if anybody wanted to include their image in tonight's report, please send them in. So that's mine. This is actually shot with an iPhone, afocal through a Celestron 9 1/4. I think I had a 15mm panoptic in there. I ran a movie. You need 3 hands to hold the phone and push the button. And so I ran a movie, and then I just went frame by frame, and I took the best one I found. Pretty nice shot, I think. And there were a couple more that were submitted to us. Glenn, you want to hit the next slide? You know which one? Oh, thank you.
Yeah.
So here's a shot by Mark Helton. You know, when I saw this slide right here, and then are we going to look at that video next? Is that video, you want to do it on the next spot? Okay. This is why planetary observing is so challenging. Look at that.
Yeah.
Right? The moon is easy. But look at how tiny Mars is. And this was very close to opposition with an apparent disk of about 14.6 arc seconds. So planets are typically pretty small. Jupiter reaches up around 50 arc seconds. Venus next month is going to be almost an arc minute across. But they're typically pretty small objects to look at, which is, you know, they're somewhat challenging. Kai sent that shot right there, and I think that's an iPhone shot also.
Yeah.
But they're fairly bright.
But they are bright, and so they hold up well against light pollution.
I love the color contrast in Marks. It's just
Yeah, I like it, and even on mine, the grayness of the moon and that little orange disc, very pretty.
By the way, Kai's, I think, was taken strictly with the phone itself. I don't know, is Kai with us?
No, I didn't see him tonight. I didn't see him.
No, I didn't know if he's on the Zoom.
But no,
Yes, I am.
Yes, go ahead. How did you take that? It's very simple.
Yeah, that's just, I took it with my iPhone to just zoom in. It's just really hard to get it focused.
Very nice done, considering.
The thing about planetary occultations is that they're pretty rare, all things considered. You know, when you think about what a planetary occultation is, it's the moon's orbital motion covers up the planet, if we're lucky, and it disappears for, you know, about as long as an hour, if it's a central, you know, occultation. So if the moon and the planet happen to be on the wrong side of Earth compared to where you're observing from, you're not going to see it. If clouds interfere, you're not going to see it. And not to mention the fact that they're fairly rare to start with. So I don't know when the next one, Mars occultation, is visible from New England, but you know, just do your homework and pay attention and be ready. You know, they're fun to watch, and that's the real reason for going out and looking at them. Benny, do you want to run that video? Just I was afraid to put it in the slide deck because sometimes videos don't transfer well. So this was a time lapse.
Did you get both entrance and egress?
I think, I don't know.
Yes, we do have both the entrance.
See, this is the video you said.
I'm going to play it fast, so.
It's amazing, it took what, about 30 seconds to cover the planet?
Yep.
Yeah. I don't know if you've ever seen an occultation, but at the last minute, it looks like the planet is the one that's doing the moving and the moon is standing still. It's kind of neat. Reminds you of that astronaut's picture of the Earth rise.
Right, it looks like Mars is actually rising above the surface of the moon, and it's actually the moon's orbital motion that's carrying the moon away from Mars itself. So they came out pretty well.
Neat stuff.
That's great.
Yeah, there's some neat stuff that came out on the internet. And again, thank you all for sharing your efforts on the internet with ATMoB Discuss or ATMoB Announce. It was really nice.
Pretty good. Thanks, Ben. And thanks, Ben, for submitting those. That's great. All right, back to the slides. So again, that's pretty cool. Is Joseph here today? Joseph Rothschild? Joseph and I actually observed Comet Atlas in the daylight. It passed close to the sun on the 13th of January. I think it was cloudy. On the 14th, I was able to pick it up telescopically. I couldn't see it with binoculars. I couldn't get a shot of it. This is here just to show you where it was in the sky relative to the sun. And I don't know if you can see it well, but that little white smudge with a bit of a tail is Comet Atlas. I was able to see it the next day. I think it was about 8 degrees away from the sun when I snapped that picture. Got a nice shout out on spaceweather.com, whatever that's worth. But it was kind of fun to see that in daylight. I first picked it up using an orange filter, because orange filters will sometimes improve the contrast on daytime objects. And so I was able to see it, get to the right spot, jiggle the telescope a little bit, so you see the movement of the object, and oh, there it was. And then I called Joseph, and because he was out doing the same thing, and then he found it, so he was happy too. So I don't know if anybody else got a chance to see that. It became the headless wonder of 2025 as it dashed into the southern hemisphere skies. The nucleus of the comet disintegrated, leaving behind a lovely tail to be seen. I don't know what it looks like these days, but it was a lovely comet for the southern hemisphere, folks.
Rich,
Yes.
what time of day did you take that picture?
Oh, it was right about noon.
Okay,
Yeah.
thanks.
So as far as the planet roundup goes, Venus is the star of the show these days. Have you seen how bright Venus is in the west?
Yeah.
Right after sunset? Man, it is just awesome.
Yeah.
Greatest brilliancy is tomorrow at magnitude minus 4.9. That is really bright. A 28% illuminated disk. The phase will only be 4% in a month at our next meeting, as Venus approaches inferior conjunction on March 23rd. Now, I've been talking this up, and I hope you've been practicing finding Venus in the daytime. At minus magnitude 5, how can you miss it, right? Just sort of look where it's supposed to be and go, oh, yeah, there it is. You can see it with your naked eye. It's amazing. But inferior conjunction on March 23rd, boy, if you've ever wanted to look at a razor-thin, giant crescent Venus, that's the day to do it. It will be 8.5 degrees north of the sun, 17 solar diameters. It's not even sport. It's not even sport. It's easy. You just have to be very careful if you're going to offset from the sun. Protect your optics, protect your eyepieces and all that.
In your eyes.
Well, in your eyes, of course, goes without saying. But at 8.5 degrees away from the sun, it's a pretty easy target. And it is well worth the effort. Make sure your telescope is pre-focused so it doesn't melt into the blueness of the sky. This morning, one of the first websites I look at every single day is Sky and Telescope. And this morning, Bob King had a nice article about the upcoming Venus inferior conjunction. So if you want more information on it, go read his article. It's a pretty good article.
I hate to be a Debbie Downer.
Sure, go ahead.
March 23rd is my birthday.
I
It's going
know.
to be cloudy.
I know. Well, it'll be pretty good the next day and the day after.
Yeah.
But like I said, careful telescope observations are well worth the effort. If you're going to offset from the sun, just be careful because I think I told you last month I lighting a finder-scope on fire, right? I told you that last month. I was looking at Venus and it looked like weird black wispy clouds. Yeah, they were in the telescope. They were in the finder scope because it was on fire. So be careful. All right, next slide. So Mercury is currently in solar conjunction, but it's got its best evening apparition for 2025 is coming up in March with greatest elongation on the 8th. 18 degrees east of the sun, shining at magnitude 0.3 with an apparent diameter of 7.3 arc seconds, 46% illuminated, conjunction with a very, very young moon on February 28th. Very challenging daytime object, but it can be done. Again, you can offset from the sun. If you have a go-to telescope, you can get onto it at that point. But remember, make sure your telescope is pre-focused. Otherwise, the out of focus image just melts into the daylight sky. Orange filter will help. But it'll be a nice sight in the evening skies in about a month. Saturn is setting really early now, only 23 degrees east of the sun, so we're about a month away from solar conjunction. So get it while you can. Rings are still only a few degrees to our line of sight. So next slide, please. What else we got? Jupiter, big and bright, high overhead in the early evening. It's currently around quadrature, 90 degrees away from the sun. And the reason I mention that is because, well, you know I like daytime observing, but if you really want to sort of enhance the view in the daytime or the late afternoon or an early twilight just before the sun goes down, is to use a single element polarizing filter and take advantage of the natural polarization of the sky. The sky's polarized. If you've ever taken a pair of Polaroid sunglasses and gone like this, you can see the effect, whereas your Polaroid glasses are one element of the filter and the sky is the other. And by turning your glasses, you can basically dial out the bright sky. If you take a single element polarizing filter and screw it into the back of your eyepiece, when a planet or a star or the moon is at quadrature, 90 degrees from the sun, that's where the sky's natural polarization is max. You can use that element, you just turn the eyepiece and sort of dial out the bright sky as best you can. Light from Jupiter will be scattered when not polarized. It's a mild filtering effect, but it really enhances the contrast. And you can actually, in early twilight, or even just before the sun goes down, see if you can spot the Galilean satellites. They're only 5th magnitude. And so with a little bit of aperture and that polarizing filter in your telescope, you can see those moons before the sun goes down. Kind of cool. There's a double shadow transit coming up on March 11th, just before our next meeting, in the late evening, but best around 11:30. I think it's Europa and Ganymede. I think it's Europa and Ganymede. But it'll be in that monthly thing I send out to you all, the great red spots and shadow transits. Mars continues to be a bit of a disappointment. Only 12.5 arc seconds. The North Polar Cap is visible. Using filters, you can improve some of the surface feature contrast. Phobos and Deimos are really challenging now. Even only a month after opposition, they're down to like 14th magnitude, maybe 13th for Phobos. Deimos is closer to 14th and a half. Pretty faint. Uranus is at magnitude 5.7, located southwest of the Pleiades cluster. So you can get out there and look at these planets. They look really cool. You guys should check them out. Next slide. So patiently waiting for T Corona Borealis. I'm going to make it no longer the variable star of the month.
That's when it's gonna go.
That's when it's going to go. If you want to keep track of it, it's coming up now at 10:30 at night. If we're here in New England, it's almost circumpolar, almost. So at 10:30 at night, Corona Borealis is coming up over the northeastern horizon. So it doesn't take long before you can actually see it, grab a pair of binoculars and check it out. If you know where to look for T Corona Borealis, right down here, you can just take a scan. Use this guy. Can you see that star compared to there? Then it's up. If you don't feel like going out, or if it's cloudy, you can look at the AAVSO website and get plots for the light. Or you can look at spaceweather.com. They put a new thing up in the upper left-hand corner of their front page that gives you yesterday's value and today's value for the magnitude of T Corona Borealis. It will go off. It will happen.
By the way, one that does something is our Corona Borealis, and that's an amazing variable star. It's usually about 6th magnitude, and it does things in reverse. It actually fades from brightness. It's the opposite of a nova. Instead of going up, it goes down. And I used to look at this star probably every 3rd night. When it does start to fade, it's kind of a slow process, but I'd look out. Usually it's about 6.1, 6.2. And then there'd be that evening, it's more like about 6:3 or 6:4. So then I'd go out maybe a couple nights later, because it's a slow process. And I stayed going to 6:5 down to 7. And that's when you get the binoculars out and you follow this thing. And it can go all the way down to 14th magnitude, which is even for a lot of the telescopes I had a 13-inch telescope, was just visible with a 13-inch telescope. And then it comes back up, but it's very, you never know. It'll go down, it'll hit maybe 10th magnitude, it'll sit there for a while, and then it might drop again, or it might go back, it might wobble. It's a fascinating star, because you don't know what it's going to do. And apparently the process, it's probably similar to what Betelgeuse did a few years ago. It belches out a cloud of dust, carbon soot, for instance, and it just kind of shades over the whole star until it finally blasts away. So it's a very interesting star. Again, if you're a binocular observer, check it out. And I used to check it out every third night. And you just get an AAVSO chart. There's a couple of stars up on the view here, and I think one is 5.8, the other one is about 6.2. And those are the two I use when I'm using binoculars. Once it starts to fade, I go to these stars right in here. Okay.
Sure, next slide, please. I think the double star of the month is the winter alberio. I don't know if you've ever heard of the winter alberio. Herschel 3945, 145 Canis Majoris. It is a beautiful double star. It's a blue and gold, it's easy to separate. Distance is about 300 light years away. And it's a relatively easy object to find. Most people ignore it because it's kind of south. And then I put as a bonus the Tau Canis Majoris cluster. As you see, 2362 is nearby, right here. That's a really pretty cluster. It's got Tau Canis Majoris is bright, and there are a little sprinkling of stars around it. I always think it looks like moths flying around a candle flame. But that's a real nice bonus. If you're going to go look at the double star of the month, which I highly recommend, just shoot a little bit further south, and you'll check out that cluster. Real pretty.
By the way, I was looking at this one, 2362, with my little 3-inch Edmund, and it's kind of weird. That star is so bright. If I looked right directly there, all I could really see was the star. A little averted vision, those stars just exploded. It was the most amazing thing to see. It was a nice sight, again with a small telescope.
It's pretty cool, and if you're using a small telescope, don't forget M41. That's a really nice galactic cluster just south of Sirius. And if you're using a little bit bigger telescope, go look at 2360. That's Caroline's cluster. Not to be confused with Caroline's rose. Caroline's cluster is a lovely galactic cluster. Relatively easy to find because it's just east of Sirius. And if you've got some aperture, and maybe a UHC or a Oxy 3 filter, you can pop off of Caroline's cluster and pick up Thor's helmet. Thor's helmet is a nice Wolf-Rayet complex and nebulosity. Pretty cool. So there's a lot going on in that slide, but do check out that double star. It's really a cool one. I'll give you a preview of next month, K Puppis. I don't know if you've ever seen that little beauty, but K Puppis is a really sweet star. I discovered that one night. I called Glenn. I said, Glenn, I discovered a double star. They call it K Puppis. Anyway, next slide. So the slides get a little jumbled up here, but so a little bit of a preview. We've got a total lunar eclipse coming up in the early morning hours of March 14th. Visible, the entire eclipse is visible from North America. So I would set your alarm clock a little bit early, but astronomy waits for no one. That eclipse will come and go. If you're there, great. If not, we'll catch the next one, 4.5 years. All right, I'll be in California, so I get to see it a little earlier in the evening than you guys do because of the time change. I'll be in New Denmark. I don't know if you heard about that in the news today, but Denmark is looking to buy California. It's on the news. It's not even fake news. It's on the news. And eclipses tend to go hand in hand. So 2 weeks after this total lunar eclipse, the next slide, there's a partial solar eclipse. If you could click the next slide, there's a partial solar eclipse on the morning of 29 March. Sunrise is at 6:32. Fourth contact in the eclipse is at 7:08. Plenty of time to pack everything up, shower, get to work or school or whatever you got planned for that day. We barely get to see it. But this is an eclipse from a few years ago. I was up at the Worcester airport because there's a nice view to the east. And I had some nice views of the sun with some clouds that morning, but it was nice. I was in the car by about 7:30 back heading home. So those are two eclipses coming up. We'll talk more about those next month. Next slide, please.
Okay, I'll
So
pick up.
you wanted to mention this as the,
This is the one that was missing last. This
Yeah.
is Doug Paul's image of 891.
Yeah.
This is the way he wanted it to be seen, so very nice job. We got a couple of Doug's pictures coming up, so we'll just go ahead on.
yeah, that's a nice shot. That's a tough galaxy to do visually. It's big, it's faint, but it can be seen. It's just a bit of a challenge.
Okay. By the way, back to the book. And as Rich was talking, I just turned, and here's a section, 2 pages on M41. And not to be outdone, they also 2 pages on NGC 2362 and the Winter Alberio right here in this book. So buy the book, and gentlemen, I won't have you stand up and take a bow, but well done. Okay, so what do we have going on now? We've got some of these objects for the winter are kind of tough. They're not easy if you're a visual observer. And I know a lot of you in the same boat I am. It's just kind of hard to get out there. The winter nights we've been having. I know Diana asked me if I've been doing any ice fishing. It's just too darn cold. And we have a great bunch of ice, but I just don't want to stand out there freezing. But anyway, this is the main object. It looks like a footprint. It's called a fossil footprint. It's about 10.5 magnitude, I believe. And actually, there's 2 as far as its sizes. There's 2 sizes. There's this part that the visual observer will see, which is about maybe 4 or 5 arc minutes across. And then there's the main nebula, and Mario caught the whole thing here. And that one's more about the size of the lunar disk. Is Mario on with us tonight?
Yes, I am.
Okay, so what are the specs here?
Well, I took this with narrowband filters, so that's H alpha, O3, and S2. It's an interesting object, so 3 hours total through the 32-inch. But notice all the Bok globules in front,
I
all those
believe,
dark spots in the
Yeah.
street. So that's a active area of star formation, I believe. The reason why the center is white is because there's hidden stars in there lighting it up. But the whole area is full of dark matter, which is a very nice area of star formation. And there's all these small ones, which are very likely to be planetary. So, nice object.
Very nicely done, thank you. We'll go to the next slide. And here's Doug Paul's rendition. You can see the footprint pretty well. It looks like one of those 3-toed dinosaur footprints right in here. Again, that's what the visual observer would see. And then the main part, again, what's the Rosetta Nebula? I think that's also about the size of the moon, I believe, a full moon. So it's probably similar in size.
A little bigger, maybe.
All right, next, we have a couple more, I believe. Dave, I'm sorry, let's back that up a minute, because Doug didn't even get a chance to tell us the specs. Can we back that up? Go ahead, Doug. What is it?
Okay, that's, 5 hours with a 6-inch aperture, and that's a wideband shot.
Okay, 5 hours, just get the time in there. Now the next slide, Dave Giordano. And Dave, are you there? Okay, what's happening, a lot of these, I've been sending these to our website, and the specs will be put on the website, so you just look when you, it's for the Observer's Challenge on the ATMoB website. You can look and get the specs on a lot of these pictures. I'll be sending those out a little later on. Next slide. The sea star. And I think it's hard to tell in that picture. I think he's still, I don't know, the field of view in a sea star is kind of large, so he's probably there. It is about the size of a full moon, and I can see the bright central part. And Dave, are you on with us? Apparently not. Now I'm going to stop here for a second because Rich knows I am a visual observer. But I bought this.
Wait, hold on for a second. Turn around. Turn around. Turn around.
What?
Turn around. Turn around. Show him the scar.
The what?
The scar.
Oh.
From the missing kidney.
Oh. No, actually, you do not have to have your kidney taken out for this. This was $500.
You will.
Eventually, $500. Now, I'm going to give you a little story on this. This is my plunge into astro imaging. It took me 5 minutes to open the box. There was a tab here. I couldn't, and I was afraid of ripping. You can see where it's kind of pulled. So it took about 5 minutes to open the box. And there are some specs. First of all, it's cold as hell. Sal called me. He called me to ask how I'm doing, and I said, I'm not. And you also butt called me twice, so it's kind of an accident. So I know I'm an ass cheek away, I guess, as far as phone calls go. But anyway, I did take the thing out the other night, and I held it like here. The manual for this is 7 pages, and you can fit it in the palm of your hand. So I had to take the manual, my glasses, and a magnifying lens to read the direction. So I'm reading the safety instructions, and it said, don't use when it's below 10 degrees centigrade. Well, that's all winter in Massachusetts, so 3 months are out right there. Then it said if it's warmer than 40 degrees centigrade, don't use it. So that wiped out the summer months. Then it said, don't use it if the wind speed is greater than 24 miles an hour. Well, they go spring and fall, so I can't use it. Well, there are probably 4 nights in Massachusetts where none of those conditions exist. 3 of those will be cloudy, so there'll be 1 night. 1 night.
The bottom line is that Glenn's got plenty of time to read that little microscopic manual. There's a bigger version online, Glenn, I've seen.
I know, that's what I'll have to do. But anyways, here's the ultimate. I'm reading, and it says, contains magnets. Keep away from cardiac stimulator. I've got a pacemaker. So, had to put the thing away. I don't know how strong that is. I'm here, still alive, so I guess it wasn't that much of a problem. Now we're just going to show you a couple things that are coming up. This is
I'm gonna help Glenn to figure
One
that
more
thing out.
slide.
Oh, but then you set one in. Okay, you did have one. Okay, because I didn't have a read. Thank you for slipping that in. What are the specs on that?
Oh, I wrote it down the bottom there. C11H, 2 hours, is an L-enhance, up to long L-enhance.
Okay. Now the next slide. I think we have our previews of what's coming up. The current challenge is in Olympus. It's NGC 1964, which is a spiral galaxy. And it happens to be right in this area, not too far. I believe that's Epsilon right there. Can't tell in this particular one. Oh no, I'm sorry, it's right near Beta. M79 is the one I was looking at. This is right up here, so it's very close to Beta. So you kind of key it on Beta and just move a little bit and you'll find it. It's a spiral galaxy. What do I have for specs on that one? It's magnitude 10.5, so it's doable. And as far as size, if you're doing it visually, it's probably about an arc minute. By less than an arc minute. That's the actual middle part right here. This is a Doug Paul image, and it's a preliminary. So he's going to send us something that will be...
That's a wide field image.
Yeah. The major part out here is more like about 5 arc minutes, so it's a little bit bigger if you take an image of the thing. And finally, just so you... by the way, on this particular one, I put this one out early because it's only in the upper part of the sky, southern sky, for a very short period of time. So I put it out last month so people can kind of catch it early. Next one.
Again, if you're going to be in the neighborhood, do check out M79.
Yeah.
It's a pretty faint, fuzzy sort of globular cluster, but it's right there. It's relatively easy to find. Remember last month, I think our Leporis was the variable star of the month. Our Leporis is just over in here, so you can find that. And then if you really want somewhat of a challenge, we don't think of the index catalog objects as being particularly bright, the IC objects. Whenever you see something as IC something, 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 you just usually write it off because it sounds like it's going to be really hard to see. But IC 418, the Spirograph Nebula, is located right in here. And it's actually pretty easy to find. If you've got a star chart, you can star hop to it. We look at it at the club all the time. It's got a nice orangish pink color if you use the right combo of aperture and magnification. It's a very nice planetary. So if you want to be challenged a little bit, go for that too.
The M79 is one of the few winter globular clusters. But coming up, go to the next slide. This is the March. I just want to get a little bit of a head start. This is called the go back a second here. That was called the intergalactic interlope or something like that. They thought it was so far away. They thought it was outside our galaxy. We now know it does actually orbit the galaxy about 3 billion years just to go around the galaxy once. It's about 10.5 magnitude, so, again, you'll need a medium-sized scope to pick it up, but it's certainly worthwhile. And the thing is this is going to be tough for star hoppers, because the nearest bright star, really bright star, is Castor down here, 7 degrees to the south of that. So when I get, and I haven't even had a chance to look at this yet, I'm going to make a finder chart that will start from here, and I'm going to just plot my way up to the nearest bright star that's in this particular area. So this will be an interesting target, yes?
I'm confused. What are these other bright fuzzies, right?
Stars.
Those are stars.
So it's going to be a nice view. You'll have 2 stars.
Why are those so...
Those are bright stars that have bloomed in the image.
Yeah.
Oh, okay.
That's why if you're a visual observer, you'd see little nice points of light, and then you'd see a little bit of this here.
Oh, I see. Thank you.
I use those 2 stars as my last star hop. I get to those 2 stars, and there's the cluster.
That's part of why I try to show them, so
Yeah.
it helps visual observers.
Yeah,
You know, it might be these two stars, I
I
can't
think
tell,
it
because
is.
that's a big chunk of a degree, but, and I think that's a, you know what the size of this field of view is here, Doug?
Tight.
Let's see,
Because those stars, I don't think those two stars are the ones in that picture.
okay, it's at most about a degree and a half.
Yeah.
Well, it's about a degree high maximum, so the width would be a maximum of a degree.
I made that star big so you could actually see it.
Oh, that's what it was. Anyway, I'm done with my spiel. I just wanted to say again, keep looking up and drive home safely tonight. And Richard still had a couple things
I
to
have
go.
one more slide, I think. Well, anyway, here are the the scheduled observing nights at the clubhouse through the end of March. We always have these, weather permitting, of course, during the dark of the moon, either the last quarter weekend or the new moon weekend. And that's when you'll find, sometimes this place is packed, sometimes there aren't very many people, but there's always somebody on duty those nights. So, you know, you can always call ahead to see if for sure there's somebody there. But watch your emails. If the weather's inclement, we cancel. But the more the merrier up at the clubhouse. It's kind of cool. It's a lot of fun. So I think the next slide is the up-and-coming star parties. Glenn, thank you very much.
Okay,
Good job. Good luck with that. Thank you.
Anand, thanks for your patience being there. The talk title is Baryons Across Time. I don't know if you want me to read this whole thing, but I will, if you don't mind. Ordinary matter composed of protons and neutrons has been a small fraction of the total energy density of the universe throughout its history. Despite its relatively small contribution, this ordinary matter is what is readily observable to us as a hierarchical large-scale structure of galaxy clusters, groups, individual galaxies, stars, interstellar medium, planets, and other familiar structures. The central theme is extragalactic astronomy has been to understand the distribution and physical state of baryons and the various stages of cosmic evolution. This baryon census has yielded profound insights into how matter has organized itself on vast cosmic scales. In this presentation, Dr. Narayanan will provide an overview of research in his field, connecting it to his own interests. Anand is a faculty at the Indian Institute of Space Science and Technology. He was a postdoctoral fellow at the Department of Astronomy at the University of Wisconsin-Madison in the US. He earned his PhD and a master's in science in astrophysics from Pennsylvania State University, in the US. He holds a BTech in Electrical and Electronics Engineering from the College of Engineering, Thiruvananthapuram. His research involves studying the physical properties and chemical abundances of gas in the circumgalactic and intergalactic space. And over to you, Anand. You are going to be the presenter now.
Since I am geographically on the other side of the globe, I thought I'll just tell you where I am located. So what you're looking at here is the southern portion of the Indian Peninsula. And the place where I work, Indian Institute of Space Science and Technology, that is located at this place called Thiruvananthapuram, right here. So which is roughly 8 degrees north of the equator. So it's a very tropical place. And our institute, it's not a big university. It's a very small institute. We have about 600 undergraduate students, about 150, 200 postgraduate students, what you would call as grad students in the US, and about 100 students who are pursuing PhD. And we have about 100 faculty. So, and it's a fully residential campus. So what that means is that all the students, they stay on campus itself. And that makes it very easy for the scheduling of classes, and that helps to carry out research throughout the clock. And this is a aerial photograph of our campus. You can see that there's a lot of greenery surrounding it, and it's a very, very small campus. It's only 50 acres across. And this institute came into existence in 2007. And we are a university under the Department of Space, Government of India. And the institute was set up with a very specific mandate, which was to provide human resource to the Indian Space Research Organization, ISRO. so which is the Indian counterpart of NASA. And ISRO has many ambitious projects that are coming up, and they wanted young people to join their workforce as scientists. So therefore, this institute came into existence in 2007. So we are only 16 years old. And over the years, the graduates of our institute, they have been placed in one of the many centers of the Indian Space Research Organization as scientists, engineers, and they have been contributing to some of the ISRO missions, both from the science point of view and from the engineering point of view. And what the greenery is because we are at the tip of what is known as the Western Ghats, which is a mountain range that runs about 1,000 miles to the southern part of India. So that's where I am located. And it's morning 7:30 a.m. here. Okay, so let me move on to the presentation. Over the years, my research has been in this very broad domain called extragalactic astronomy, observational extragalactic astronomy. And while during my time in the US as a postdoc, I was working largely on doing an observational census of baryons in our universe. And baryons, for those of you who do not know, it's just a fashionable word for protons and neutrons. So the ordinary matter that we are all made of, and all the things that are around us is made of, it's all made of atoms. And as you know, the fundamental ingredients of atoms, the subatomic particles, are protons and neutrons. So baryons across time is a reference to how ordinary matter has transformed itself, how it has evolved over cosmic time, over the last 13 billion year history of the universe. As it turns out, this is a very interesting line of research for the following reason. If you ask this question of where are the luminous structures in the universe? When I say luminous structures, I mean structures that are emitting electromagnetic radiation, that is light, which are the stars, the interstellar medium, the galaxies, which are conglomerations of stars. If you ask this question, where are the luminous structures located? How are they distributed in the universe? Then, as it turns out, it's very easy to answer that question for the nearby local universe for obvious reasons. It's much more easy to look at light that is coming from the nearby universe. The big questions, the unknown, are in the high redshift universe and the distant universe, where we don't really, it's very difficult to see young galaxies forming, young galaxies coming together to form groups and clusters. So the big questions are all in the high redshift universe, and in the low redshift universe, the information about galaxies is pretty much well understood. But if you now change this question and ask, where are baryons located in the universe? Baryons are the stuff out of which galaxies, stars, all these things are made of. So if you ask this question, where are baryons located? As it turns out, it's much more easier to understand where baryons are in the high redshift universe, in the distant universe. It's much more difficult to figure out the distribution of baryons in the more local, low redshift universe. So as you know, redshift is often used as a proxy for distance in astronomy. The higher the redshift, the further back in time we are looking. So the high redshift universe, we have a fairly good understanding of the distribution of baryons. In the low redshift universe, as it turns out, there are some challenges. There are some barriers that prevent us from fully understanding the distribution of baryons. So this presentation is going to be largely on that, and I'll touch upon the areas where we have tried to contribute. So this pie chart that you're looking at, I'm sure all of you would have seen a pie chart like this. This basically tells us the ingredients or the constituents of our universe as told to us by cosmology. So the major part of the pie chart is taken up by dark matter and dark energy. Dark matter forms the scaffolding on which ordinary matter is sitting. So whenever we are looking at a galaxy, we have to, in our mind, we have to imagine that this galaxy is kept intact because it is under the gravitational potential of an unseen entity, which is what dark matter is. And dark energy, as we understand it today, is what is causing the accelerated expansion of the universe. So those are those two components which are occupying most of this pie chart. And a tiny portion of the pie chart is taken up by baryonic matter. Here it is marked as atoms, but a more correct representation would be baryonic matter, protons, neutrons, even if they are not part of atom, even if they are existing as free entities, they are all lumped into these atoms. And we know through multiple lines of evidences, primarily by looking at the elemental abundances of light elements like deuterium to hydrogen, helium to hydrogen, etc. in the universe, we know how much of baryons are present in total in the universe. So that is given by this term called the baryonic density parameter, omega B. So some of you would be familiar with what this term is. Essentially, it's telling us the repository, the reservoir of baryons that is available to us in the universe. So throughout cosmic history, that's the sum total of baryons that we have. And the result of structure formation is to basically reorganize baryons into different forms and shapes. Okay. By the way, I just wanted to mention here that it's mentioned mass, energy, density in the present universe. So for those of you who are not familiar with this, see, this represents what the ingredients of our universe are if you take a representative volume of the universe. So when I say representative volume, what I mean is the room that we are sitting in, for example, does not represent the universe. It's a very cozy environment. Probably there are about 1 trillion or more particles of molecules of air in the room that we are sitting. The temperature would be something that's very comfortable, maybe like 70 degrees Fahrenheit, or depending on the time of the day, whether the air conditioning is on, etc. But that's not representative of the universe. If you go away from solar system, if you go away from the Milky Way galaxy, if you go into the far depths of space, and if you take a volume there, then this is the composition that you're going to encounter. The room that you're sitting in, this is not going to be the composition, because it's a very, I don't want to use the word synthetic, but it's a very different kind of environment. Okay. So for us to understand how the baryons have transformed themselves into different structures in the universe, we can get some initial clues by looking at the cosmic microwave background radiation. So this is an all-time map of the CMB. CMB is essentially the oldest photons that are coming towards us or available to us. The cosmic microwave background photons are about 13 billion years old. They come to us from a time when the universe was only 300,000 years old. So it's a very, very young universe. And this shows this is an 8-off projection of the CMB, the cosmic microwave background. And the color coding shows the intensity of the CMB in different directions in the sky. So what when we measure the intensity, we can convert it into temperature. So one can also plot a temperature map like this. And as you can see, there are 2 different colors that are dominating this plot. One is blue, the other is kind of yellowish red. And they represent, and they are spread out throughout the map, and they represent density inhomogeneities or density anisotropies in the early universe. Okay. So the regions that correspond to blue are regions which had a slightly lower density compared to the average density of the universe, and the regions which are yellowish red are the ones which had a slightly higher density. So when we measure the intensity of CMB across the sky, we see these anisotropies, and the anisotropies, sometimes they are called density fluctuations, sometimes they are called temperature anisotropies, they are also referred to as density inhomogeneities. So they are at a very tiny, small level. The amplitude of this is a 1 part in 100,000. So these are not major fluctuations in density, these are tiny fluctuations in density. And the CMB is telling us that when these photons started free streaming through the universe, from an epoch, from a time when the universe was only 300,000 years old, at that time, matter was not uniformly distributed in the universe. There were tiny density inhomogeneities or anisotropies at the level of 1 part in 100,000. And these density anisotropies or inhomogeneities are crucial because we need them to explain the formation of large-scale structures in the universe. Without these density inhomogeneities, we don't have an initial starting criteria from where you can build upon the formation of structures driven by gravity. So that's exactly what cosmological simulations done with supercomputers do. So what I want to show you now is some screenshots from a very famous cosmological simulation done at Max Planck Institute. So what you are looking at here is basically a computer visualization of the initial conditions in the universe. You see that there are some regions which are black and some regions which are red, and so they represent the kind of CMB anisotropy that you saw earlier. They represent the tiny density fluctuations or inhomogeneities in the early universe. So using these as the initial condition, or using these as the starting criteria of these simulations, with gravity as the driving force, these computer simulations try to see how these density inhomogeneities get amplified over time, driven by gravity. Okay? And so if you were to fast forward the simulation, you would see that with the passage of time, which is represented by the redshift number at the top of the panel, Z is what redshift represents, and the lower the number, the older the universe is. So you can see that the regions which were slightly overdense start becoming more and more overdense, and their matter starts flowing in, and that's where galaxies, galaxy groups, galaxy clusters, and superclusters begin to form. And then they are connected by this intricate filamentary network of sheets, which is referred to as the cosmic web, with other galaxy clusters, other galaxy groups, etc. So this is what is very poetically referred to as the cosmic web structure of our universe. And so the reason for showing this is to communicate this fact that from a simulation point of view, from a theoretical point of view, we now have a fairly good understanding of how, starting from very simple initial conditions, you can produce the large-scale structures that we see in the universe. So there is some understanding of how dark matter and baryons have self-organized over a period of time. Now, so I just forgot to mention that if there are any questions at any point, feel free to interrupt, and I'll be happy to answer them to the best of my ability. So the questions that we are addressing is, where are the baryons at different epochs in the history of the universe? So one possibility is that these baryons could be present inside galaxies in the form of collapsed objects like stars, planets, compact objects like neutron stars, black holes. Then there could be a lot of baryons present in the interstellar medium in the form of gas and dust. There could also be ordinary matter present in the envelope surrounding galaxies. This is called circumgalactic medium. And then there could also be a large number of baryons present in the space that separates galaxies, which is known as the intergalactic medium. And if these galaxies are existing in a group, it's called intra-group medium. And if these galaxies exist in the form of a cluster, then it's called intra-cluster medium. So these are the possible locations where we expect baryons to be present. Now, so if with this information, if we now try to do an observational census of where the baryons are in the universe, in the distant universe, and in the present universe, we get the following results. So first, let's deal with the distant universe. So what we have here is a Hubble deep field image taken by the NICMOS camera on Hubble Space Telescope. And whatever you see a bunch of galaxies in it, and whatever is circled with that green circle, they are all very high redshift galaxies. These are galaxies that are at redshift 6, 7, 8, 9, etc. And now JWST has pushed the upper limit of the highest redshift galaxies to even higher redshift, but this particular image is of HST. So the reason for showing this image is to tell you that through such deep imaging, it is possible to pick out galaxies in the very high redshift universe, and also through photometric observations, it's possible to get the photometric redshift, which means where they are located in the universe. That information is also accessible to us. So once we have a data like this, we can construct what is known as a galaxy mass function or a galaxy luminosity function. So this graph, we need not worry about the details in it, except that the different curves represent different galaxies present at different redshifts. Z is equal to 0 would be the present universe. And as you go higher in number in redshift, we are looking at the distant, farther away universe. Along the vertical axis is the number of galaxies that are present in a cubic megaparsec volume of our universe, so megaparsec cube. And along the horizontal axis is the amount of mass that is locked up in stars, okay, the stellar mass. So as you can see, you take higher redshift universe, Z is equal to 8 or something. We know that there are large number of low mass galaxies and fewer number of intermediate mass galaxies and fairly small number of high mass galaxies. So this, using a galaxy mass function like this, it is possible to therefore count the number of galaxies that are present at a given redshift, because you have the number density, and then convert it into a mass estimate. And from that mass estimate, you can estimate how much baryons are present. And if you do that, you find that the amount of baryons that are present in galaxies in the form of stars and interstellar matter is about 2 to 3% of the total amount of baryons that are available in the universe. So only about 2 to 3% of baryons in the high redshift universe are inside galaxies. And that is expected because high redshift universe means the universe is very young. So galaxy formation is still ongoing. The universe had not had enough time to form galaxies. So most of the baryonic matter, we expect it to be outside of galaxies. And so it's fairly intuitive that therefore these numbers would be small for what is present inside galaxies. So now if you want to look at what is outside galaxies, you cannot do it with imaging. The reason is because the stuff that is outside of galaxies in the intergalactic medium is in a very diffuse form. So to give you an idea of how diffuse it is usually the density in the intergalactic medium is about 10 to the minus 4 to 10 to the minus 5 particles per centimeter cube. So that is like one particle in 100,000 cubic centimeter volume, which is much less dense compared to even some of the best vacuums that you can produce.
Your slide disappeared.
Yeah, this slide is blank. There's going to be a video that will be played.
All right.
So I just want to talk before I play the video. So since these baryons are in a very diffuse form, they are not emitting starlight. So if you point a telescope with a camera connected to it and take an image, we will be missing out on these diffuse baryons. And so we have to resort to other techniques to find these diffuse baryons. And one such very powerful technique is quasar absorption line spectroscopy. So quasars, as most of you probably know, are very distant bright galaxies. They have a very active nucleus, which makes them extremely bright. And since they are extremely bright, we can detect them over a large distance, even if they are at a very large distance. So what astronomers do is they use quasars as like background beacons, as like a torchlight. And the light from the quasar, from a very far away, far distant quasar, as it travels towards Milky Way, as it travels towards us, every parcel of gas that intercepts the line of sight towards the quasar is going to absorb photons from the light that is emitted by the quasar. So if you now record a spectrum of the light from the quasar, a spectrum is nothing but, you collect the light and you disperse it, the light, you spread it into its component wavelength with the help of an instrument called spectrograph. So you have a spectrum. So once you record the spectrum of light from the quasar, you are going to see absorption line, like spectrum emitters of material that absorbs photons, and this material is between us and that quasar. Some of it could be gas that is present in the Milky Way galaxy itself, but a large fraction of the absorption lines are going to be material present in that quasar. Sorry, but there's some kind of a background noise that is coming through. I don't know if it's just me or somebody's microphone.
Yep. Yeah, that was the building.
Yeah, okay, sorry, thank you. Yeah, so this is the idea, this is the essence of quasar absorption line spectroscopy. So we are not interested in the quasar itself, but we are interested in the quasar shining through the universe. And so by looking at the light from the quasar, we get to know what is between us and that quasar. So this is a very effective way to study diffuse gas in the universe, gas which is not emitting light. So if that gas is made of hydrogen, carbon, nitrogen, oxygen, and similar heavier elements, all these elements are going to absorb selectively certain wavelength photons, and they will leave their own unique spectral fingerprints in the light of that quasar. And by analyzing that, we will get to know the physical properties and the chemical abundances present in the gas that is not emitting light, this diffuse gas, intergalactic medium. So using this absorption line technique, astronomers have tried to complete the observational census of baryons in the high redshift. So we know that about 2 to 3% of the baryons are inside galaxies emitting light. Now, what about the remaining stuff? So for that, they use quasar absorption line spectroscopy. So what you're looking at here is a graph that shows how a typical spectrum of a high redshift quasar is like. So along the horizontal axis is wavelength in units of angstrom, and along the vertical axis is how bright the quasar is at those wavelengths. You see a large peak over here, and that is the hydrogen emission from the quasar itself, the atomic hydrogen present in the quasar itself. And blueward of that emission, one sees a forest of lines, this densely packed set of lines. So these lines are produced by hydrogen that is present between us and that quasar. Some of it could be hydrogen within the Milky Way galaxy, but a lot of it is hydrogen that's present in the intervening space. And redward of it also, you see some absorption lines. Those are predominantly coming from metals, heavier elements that are present in those clouds that are between us and those quasars. So the redshift comes into picture here, because redshift can shift the location of lines from where they are supposed to be in the laboratory frame. The lines are all jumbled up in the quasar spectrum. So if you now zoom into this forest of lines, that is what is shown in the slide down, you can see that this forest of lines is composed of several individual absorption lines. So a lot of them is from hydrogen. And so if you now start counting how many hydrogen lines are there, and convert it into a column density of hydrogen, how much hydrogen should be present to produce an absorption line like this? How much hydrogen should be present to produce an absorption line like this? So if you now do that painstaking calculation, then you can convert that column density, that total column density, into an baryon estimate corresponding to the amount of baryons that is present outside of galaxies in a diffuse form. Okay, so that is the idea. And these lines are primarily tracing the intergalactic medium hydrogen, and this intergalactic medium exists at a temperature of about 10 to the power 4 Kelvin. The reason why it has this temperature is because it is ionized by photons that are produced by luminous objects in the universe. So therefore it's called photoionized gas, and it has temperatures of that order. So keep this temperature in mind, because later on we are going to see that the situation will become much more complex when we look at the local universe. So there are equations that one can use to convert the amount of hydrogen that you observe in the Lyman alpha forest into a baryon number, baryon estimate. And these baryon estimates show that, show that 97% of the baryons in the high redshift universe is in the intergalactic medium. So if you now pause for a second, and if you look at the census of baryons and high redshift, what observations are telling us is that these luminous galaxies, which are just forming a high redshift universe, they contain within them are about 2 to 3% of the total baryons, and the remaining 97 baryons are to be found in the photoionized phase of the intergalactic medium, which has a temperature of about 10,000 Kelvin. So if you want to make a pie chart of the observational census of baryons in the high redshift universe, this is how it's going to look. Inside galaxies, 3%, outside of galaxies, 97%. So it's a closed chapter now. When we're done the census, it's done. Now, we fast forward to the present universe, to the local universe, and what has happened from the early universe to the present universe is structure formation has happened. As we saw earlier, starting from tiny density inhomogeneities, large-scale structures have formed. When I say large-scale structures have formed, what I mean is that these then overdense regions started aggregating more and more baryons and started forming galaxies, galaxy clusters, etc. And so here you are seeing a computer visualization of that process happening. There are many flavors of these simulations, with different set of initial conditions, different resolutions, different microphysics, but the end result is more or less the same. So the high redshift universe, if you were to use quasar absorption line spectroscopy, then what you expect is the line of sight is going to pass through a lot of gas in the intergalactic medium, because that's where most of the baryons are. Now you fast forward to the present universe. Because of structure formation, you expect a lot of baryons to have flown into galaxies and galaxy clusters and groups, and the intergalactic medium should have thinned down. So that's what the simulation is showing. This is high redshift universe in a box. This is low redshift universe in a box. So when you throw a line of sight through this, you expect to see fewer number of absorption lines in quasar spectra corresponding to atomic hydrogen in the intergalactic medium. So that's what actually observations show. So what you are seeing in the bottom panel is the spectrum of a quasar at high redshift, and blueward of the hydrogen emission from the quasar itself. One sees these forest of lines which are produced by hydrogen in the IGM. Now, if you take a low redshift quasar, this is the hydrogen emission from the quasar itself, and that low redshift quasar is, the line of sight is primarily passing through the low redshift universe, the present universe, and you see that this forest of lines have kind of disappeared and there are fewer lines. So that is consistent with what we expect, because structure formation have taken matter from the IGM and that they have put it into galaxies. So therefore, people have done a similar Lyman alpha forest survey, an IGM survey in the low redshift universe. Now, the only difficulty of doing this is if you want to look at hydrogen, atomic hydrogen in its ground state, then you need access to ultraviolet wavelength, because atomic hydrogen transitions in the ground state happen in the UV part of the electromagnetic spectrum. And since UV is cut off by the Earth's atmosphere, we need access to space. Only from a space-based observing platform, it becomes possible to observe IGM, intergalactic baryons, in the low redshift universe. So one had to wait for UV spectroscopy to be done from space to do this. And with IAU and with FUSE and with HST having UV spectrographs, it became possible. So when they did this observational census of baryons in the IGM in the low redshift universe, they found out that indeed from high redshift, which is the right extremity of the graph, to low redshift, the amount of baryons in the low redshift universe is decreasing. But when they looked at by what amount it has decreased, they found out that the photoionized IGM has about 30%, 28 to 30% of the total baryons. In the high redshift universe, they had about 97%. In the low redshift universe, it's 30%. So the amount of baryons in the IGM, the photoionized phase of the IGM, has come down. So naturally, you expect the remaining amount of baryons to be inside galaxies in the form of stars, interstellar medium, etc. So that is what you expect. So it's much more easy to observe galaxies in the low redshift universe. So the census of baryons inside galaxies is much more easier, because you can even see the faintest galaxies in the low redshift universe by virtue of being closer to us. So what you're seeing here is similar to the graph that you saw earlier. This is a galaxy mass function for the low redshift universe. On the vertical axis is the number of galaxies that are present in a cubic volume of space. And around the horizontal axis is the amount of mass that is in the form of stars. ISM also you can include in that. And so through observational surveys like this, it's possible to estimate the total amount of baryons inside galaxies in the low redshift universe. And when they did that, they found that only about 10% of the baryons are inside galaxies. Okay, so now if I were to put that picture together, 10% of ordinary matter is inside galaxies. From 2% in the high redshift universe, it has increased to 10%. And 30% is in the photoionized phase of the IGM. So 30 plus 10 is 40, which means 60% of the baryons have not been observed, okay, for the low redshift universe. And the other fact is that even after 13 billion years of history, only 10% of the ordinary matter has gone into galaxies, which means that at some level, galaxy formation is a very inefficient process. The universe had 13 billion years, and still it could, the gravitational potential wells created by dark matter could only pull together about 10% of the total baryons. So that leaves us with an interesting question. Where are these baryons, remaining 60%? Okay. So as it turns out, we know more about the distant universe when we look at baryons than we know about our own local universe. So therefore, this became an interesting problem. It got referred as the missing baryons problem, and it became one of the central theme of research in extragalactic astronomy. One of the instruments on the Hubble Space Telescope on its last servicing mission that happened in 2009, one of the instruments that was installed was the Cosmic Origins Spectrograph. This Cosmic Origins Spectrograph was installed with one of the primary science objective behind it was to take very high sensitivity, very high signal to noise spectra of quasars at far ultraviolet wavelengths, so that we can do a proper census of baryons in the low redshift universe. So I'll talk about it in the forthcoming slides. So answer to the missing baryons problem lies in understanding how structure formation has unfolded in the universe. So we don't know where the 60% of baryons are from an observational perspective. So what do? We take refuge in simulations. We go to simulations and we ask the simulation, so can you tell us where these baryons are lurking, where these baryons are hiding? So what you're looking at here is a visualization from the Illustris simulation. On the left side, you're seeing a box of the universe that is evolving with time. And what is shown here is how dark matter is self-organizing itself under the influence of gravity. And on the right-hand side, if you put ordinary matter into those dark matter potential wells, then the right side panel shows what is happening to that ordinary matter. That is baryonic matter. And here, the visualization shows the temperature of that ordinary matter, where blue and cyan represent cooler phases of gas, and red and yellow represents warmer and hotter phases of gas. So, and time is progressing, as you can see in the bottom panel. Redshift is decreasing, which means time is progressing. So we begin to see that the structure formation you can see on the left panel where dark matter is self-organizing. But if you now shift your attention to what's happening to the baryons, you begin to see that as galaxies and large-scale structure forms, the amount of baryons that are in warm and hot phases, the amount of baryons that are at temperatures greater than 10 to the power 4 Kelvin, that fraction is increasing. That's what the red and the yellow is representing. And these structure formation simulations tell us that the reason why this is happening is because as dark matter self-organizes itself, as dark matter clumps together, creating deeper and deeper gravitational potential wells, ordinary matter starts flowing into these dark matter potential wells. And when ordinary matter flows into these dark matter potential wells, if the speed with which they flow exceeds the speed of sound in that medium, whatever medium is there in the intergalactic space, if it exceeds the speed of sound in that medium, then it produces shocks, astrophysical shocks. So when a disturbance propagates through a medium with a speed exceeding the speed of sound, then that's the condition for shock. So astrophysical shocks are produced, and the shocked gas, the post-shocked gas, gets heated to these kind of temperatures, which are in excess of 10,000 Kelvin, typically temperatures of 100,000 to 10 million Kelvin. So this phase of the intergalactic medium was not present in the high redshift universe because structure formation had just started. 13 billion years of structure formation led to the reorganization of baryons such that you have the amount of baryons in galaxies increasing from 3% to 10%. You have the amount of baryons in the cooler phase of the intergalactic medium traced by the Lyman alpha forest decreasing from 98% to about 30 to 40%. And now because of structure formation, a lot of baryons are now occupying this new phase of the IGM, new density temperature structure of the IGM, which is referred to as the warm hot intergalactic medium, or WIM for short. This phase was not existing in the early universe, and it's a new phase that has been created. And that's what this green graph shows. So simulations tell us that that is where you should look for. If you want to complete the observational census of universe in the low redshift universe, you have to have lines. You have to look at lines that are diagnostic of these kind of physical conditions. Lines that trace absorption lines from chemical elements that trace gas with temperatures of 100,000 to 1,000,000 Kelvin and even larger. Now, the only problem there is that at those temperatures, all the hydrogen is going to be collisionally ionized, which means that the hydrogen is going to be ripped off its electron and it's going to be just a bare proton. So with a bare proton is not going to absorb Lyman alpha or any of those typical electronic transitions because the electron is no longer bound to the atom. So therefore, we have to use metal lines, heavier elements, which can be present in these kind of physical conditions. And the bottom line is that you have to look at regions outside of galaxies if you want to know where the baryons are. And one more just small point which I want to mention here is galaxy formation is a very complex process. And what is shown here in this artistic impression is a galaxy in the middle and the way the baryons are getting recycled and accreted in a galaxy. So a galaxy is constantly trying to pull together matter from its local environment. So this will be pristine gas that is unpolluted by the products of star formation, gas that does not have much metals. And star formation is happening, and when high mass stars go supernovae, when there are multiple high mass stars going supernovae in the same region of space, then that's going to inject a lot of energy and momentum into the ambient medium, which is going to throw stuff out of the galaxy. So there is material that is flowing out of the galaxy into the intergalactic medium. Some of that material may rain back down on the galaxy. There is also gas that is getting accreted. So the environment around the galaxy is also a huge reservoir of baryons. The environment away from galaxies is also a vast repository of baryons. So we have to look at all this. So again, the observational strategy remains the same. How do you want to, if you want to detect these diffuse baryons, you have to use quasar absorption line spectroscopy. So the way it is done is, imagine that this is Milky Way, then we try to find bright AGNs, bright quasars at different redshifts, low redshifts, high redshifts, etc., that can be readily observed with ground-based optical telescopes with optical spectrograph and space-based telescopes with ultraviolet spectrographs. If you want to observe a quasar in ultraviolet, then the quasar itself has to be bright in ultraviolet, because only if the quasar is emitting an ultraviolet, you can see it. So you have to select UV bright quasar. So there's a lot of selection process that goes into selecting these targets. And each line of sight gives us information about what is present between us and that quasar along that line of sight. So the drawback here is that you have information only along one dimension. You don't have information along 2 dimensions or 3D. You only have a pencil beam that connects you to the background quasar. To get over that limitation, what you do is you don't restrict yourself to one observation. You pull together a large number of quasars along different lines of sight, so that you have a statistically significant sample of absorption systems with which you can do physics. So anything that is intercepting the line of sight is going to selectively absorb photons. They could be individual galaxies, they could be a circumgalactic medium of galaxies, they could be gas between galaxies in intergalactic space, they could be intra-group or inter-cluster gas. So just to spell it out, use ground-based and space-based quasar spectroscopic data. If you're lucky, you can have proprietary data from these observatories. Or otherwise, all these observatories are very generous. They put out all their data in the public domain for people to use. So a lot of secondary science can be done with that. And using absorption line spectroscopy from these observatories, we try to identify gas at low redshifts that belong to circumgalactic medium, intergalactic medium, intragroup medium, intracluster medium, and we carefully analyze these absorption lines and try to determine the physical properties and chemical abundances of this gas. So just to push this forward, there are only a couple of more slides, and then we can move on to the question and answer and interaction. So as I said, if you want to complete the baryon census, we need lines that would give us information about the warm, hot intergalactic medium, this new phase of baryons that have come up because of structure formation. Hydrogen is completely ionized at those temperatures of 100,000 to 1,000,000 Kelvin. So we need other lines. And what is shown here along the vertical axis in logarithmic space is the temperature of gas. So 5 would mean 100,000 Kelvin, 6 would mean 1,000,000 Kelvin. And along the horizontal axis is density of gas in terms of particle number density. So 0 would mean, this again in log space, so 0 would mean there's like 1 particle per cubic centimeter. -2 would mean that there are about 1 particle every 100 cubic centimeter, so on. And what is written over here, for those of you who are not familiar, these are spectroscopic notations of chemical elements. Astronomy being a very old science, the modern physics would write atoms and ions as 0 and plus, etc. For example, atomic hydrogen will be H with a 0, ionized hydrogen will be H with a plus. In astronomy, we still use the old notation where neutral is represented by H with a Roman numeral I, and ionized would be with 2, 3, 4, etc. So what you're looking at is ionized chemical composition, and the gas phase that we are interested in is this gas that is at temperatures from this 10 to the power 5 to 10 to the power 6.5, etc. So you can see that there are some ions which we can go after. For example, oxygen is a fairly abundant element in the universe, and 5 times ionized form of oxygen is a line that can be used to detect this million Kelvin astrophysical plasma. Neon is not that abundant, but it has a very interesting doublet line in the ultraviolet part of the electromagnetic spectrum. So we can use that as well. So with the using some of these, by picking some of these lines, we can probe the warm-hot intergalactic medium and try to get an observational census of it. Just skip this slide. So for my own work, I have been primarily using archival data from the Keck Observatory. There is a spectrograph, optical spectrograph called HIRES on Keck, high resolution Echelle spectrograph. And I also used a lot of archival data from the Very Large Telescope VLT, which is an ESO observatory in Chile. And VLT has a spectrograph called UVES, ultraviolet Echelle spectrograph. So these give us optical spectra, and for space-based from space-based observatory, we get this ultraviolet spectra, both from the STIS and the COS instrument. So while I was a postdoc at the University of Wisconsin-Madison, I had the fortune of being a part of the COS science team. So as the cosmic origin spectrograph was switched on after its installation in 2009, some of the early observations of UV bright quasars to study the warm-hot intergalactic medium in the low redshift universe, that happened with the COS science team. So I was also part of it. And I've continued that train of work for some more time. So in the remaining couple of slides, I'll just show you snippets of results. I'm not going to go into details of it because Venuji had told me that this is a very heterogeneous audience. So I'll spare the details, but if anyone is interested, I'll be happy to talk more about the details. So what we have done is we have used quasar absorption line spectroscopy to go after lines of ionized oxygen, ionized neon, thermally broad hydrogen, magnesium 10, etc., and carefully disentangle the physical conditions in those absorbing gas phases. So these absorption lines look like this. Just wanted to show you some real data. So what you're looking at here is along the vertical axis is the brightness of light that we are seeing from the quasar. And you can see that there are 2 lines of 5 times ionized oxygen. That is what is written as oxygen 6. 1031 and 1037. These 1031 is the wavelength of that line in units of angstrom. 1037 is the wavelength of this line in units of angstrom. So just by looking at the wavelength itself, we can see that it is in the ultraviolet. So we have to have access to UV. And this oxygen 6, if you carefully model the origin of this oxygen 6, what kind of physical conditions can produce this oxygen 6, you'll come to the conclusion that you need gas warm hot plasma, which is collisionally ionized, not photoionized, which is collisionally ionized to produce this kind of an oxygen absorption. To show you a couple of more examples, this is another example of an oxygen 6 and a neon 8. Neon 8 is neon, which is 7 times ionized. So 7 electrons have been ripped off it. So it's a pretty highly ionized state. And the fact that it is a highly ionized state itself says that this ion is tracing gas that is very hot in its plasma form. And when you combine the physical conditions that is needed to produce oxygen that is ionized and neon that is ionized, you get the kind of conditions that you expect for the warm hot intergalactic medium. Just a couple of more examples. Other ions can also be used. So instead of taking you one by one through what work we have been doing, I just put together a collage of spectroscopic data from our works. So in each panel, you can see a host of lines, absorption lines, all occurring in the low redshift universe. And we have used these absorption lines. We have measured the column densities of the chemical elements that are present to produce these absorption lines. Then we resort to ionization modeling. We do some radiative transfer calculations, some ionization modelings to pull out the physical conditions, the density, the temperature, the pressure, the line of sight thickness, and the chemical abundances in the gas that is producing this absorption feature. Okay, so that's the kind of work that goes behind the scene once you extract data from observatories. And using lines which are diagnostic of WIM-like physical conditions, we have detected several examples of absorption which are reminiscent of the kind of physical properties that is present in the warm-hot intergalactic medium. And as I mentioned, the region surrounding galaxies is also important because there's a lot of recycling of gas that happens. So we have also been working on lines of sight, quasar lines of sight that pass through galaxy halos, trying to understand how baryons are distributed around galaxy halos, because that's also a region that simulation says where you expect a lot of baryons. So what is shown here is results from one of our recent papers where we have an absorption system that we have studied using data from ground-based and space-based observatories. And on the right-hand side, what you're looking at is integral field unit spectroscopic data from VLT. So IFU, most of you would be familiar with it. IFU is basically nothing but, I mean, in astronomy, you can think of imaging. So when you take a picture, you have a 2D information of the sky. And when you record a spectrum for any of those objects, you know how bright it is at different wavelengths. Now you imagine putting these two together. So what you have now is a data cube where you have an image, and along the third, which has 2 dimensions, and along the third dimension, you have wavelength information also. So every pixel in that image can be extracted to get a spectrum. That is what integral field unit spectroscopy is. So many of the great observatories have, ground-based observatories have now an IFU component in it. And so this data of these galaxies that are responsible for producing this absorption, what you're looking at is IFU data, where you can do a lot of things. You not just look at the galaxy, but you can estimate what is the rate of star formation in that galaxy, whether that galaxy is capable of driving these winds because of supernovae, how is the galaxy rotating, and whether the gas kinematics that you observed in absorption can be connected with how the galaxy itself is rotating. So there's a lot of morphological kinematic analysis that you can do for the absorption and galaxy and compare them and try to detect the baryon reservoirs in the envelope regions around galaxies. So just to summarize some key takeaways. Okay? So the intergalactic space within galaxy groups, and these are some of the results that come from our publications, and there have been substantial results from other groups also. So I'll just leave the slide there. There's nothing much to explain. We have had several detections of WIM in the low redshift universe. We don't have a full observational census of WIM yet because these are very difficult measurements. But, and in terms of takeaways, if you want to remember a few points from today's presentation, these are some takeaways. Okay. So throughout cosmic history, ordinary matter has lived outside of galaxies. Stars and ISM trace only about 10% of baryons in the present universe. So when we look at a beautiful image like the Hubble Deep Field, which is sprinkled with these galaxies in all kinds of orientations and sizes and shapes, we have to remember that what you're looking at is the tip of the iceberg in terms of baryons. Vast majority of baryons have always lived outside of galaxies. In the high redshift universe, that is very much true, because 98% of the baryons are outside of galaxies. Even in the low redshift universe, majority of the baryons are in spaces between galaxies and in regions surrounding galaxies. So galaxies only provide you with a very biased view of how ordinary matter is distributed. At high redshift, the properties of this diffuse gas is easier to understand, because most of these baryons are in IgM and it is in a single phase called photoionized phase with a temperature of 10,000 Kelvin approximately. At low redshift universe, ordinary matter is in a complex mixture of temperature and densities. You have gas in the IgM at 10,000 Kelvin. You have gas in all kinds of temperatures between 10 to the power 4 Kelvin and 10 to the power 7 Kelvin. So you have this new phase called WIM that has come up. Quasar absorption line spectroscopy is at present one of the most efficient ways to study bulk of the matter in the universe at all epochs. So with this, I will stop and I'll be happy to take questions.
Very interesting. questions? One thing you determined is that in order to look at the local distribution, you have to look at basically metals, meaning things that are not hydrogen or helium, because of the ionization states that you would see. What happens when you look at the remote universe, that is the high redshift regions, using some of those tracers? To what extent, we should expect less metals, because there should be there's less expulsion of stuff from supernovae out there, but do you actually get to see that change as well?
Yeah, so great question. So as you mentioned, metals are put in the universe because of the nucleosynthesis that is happening inside stars. So stars are the places where metals are synthesized, and when these stars die, they throw out these metals. So what we expect is that the overall metal abundance in the universe would gradually increase with time. In the early universe, there were very few stars, so the gas was primarily pristine with lesser metal content, and with time, you will have the metal abundance increasing. And that's indeed what we observe. So if we use some of these metal lines of carbon, oxygen, nitrogen, etc., and try to determine how much of those lines are present in the high redshift universe and convert that measurement into a mass density of metal, a mass density of baryons that are locked up in the form of metals, then we find that the high redshift universe, it's very less, and over a period of time, the amount of baryons that are present in the form of metals is gradually increasing. But that number, the absolute number, is very, very small. Most of the ordinary baryons are still in the form of hydrogen.
Thank you.
Question? This doesn't directly address the area of your research, but why do baryons exist? I mean, at the beginning of the universe, when inflation happened and expelled lots of energy, there should have been equal numbers of particles and antiparticles, baryons and antibaryons, which should have annihilated. But obviously that's not what happened. So what could have given rise to the excess of baryons?
Great. So I think that's a very profound question. It's at the centerfold of cosmology, that question. So if there were equal number of particle and antiparticle, then you would expect them to annihilate. So, but we do see matter all around us. So that means that there was at some place, there was a breakage of the symmetry. For some reason, there were slightly larger number of particles compared to antiparticles. Now, why that symmetry breaking happened, there are some explanations for it. I'm not able to quickly recall off the top of my head what those explanations are, but probably if you look into popular science books, they explain it very well. I don't exactly remember why the breakage of the symmetry happened. Maybe somebody in the audience would know this. I don't know if anyone wants to look into this.
Any more questions from the online?
I don't see any hands raised.
You have?
No.
Thank you, Dr. Anand.
Thank you.
So
I can log off now.
Well, yes, maybe. Yeah, I think you're good. Thank you so much.
Thanks everyone. Thank you.
That's fantastic.
Great. It was a great time.
Have a nice day.
Yeah.
Have a good day.
Just another reminder about the black ice outside.
Yeah.
It's extremely dangerous.
So here, yeah.
You're not gonna make it to the car.
I think you're good, Abby.
You have to
Have a
say.
good evening. We'll meet to March 13th, 8 p.m.